we are once again. Welcome to the physics video lecture. This is Psci 168, video lecture 38. This is the penultimate lecture. The final one, our final hour, will just be review and discussing what is going to be on final exam. But right now, we want to talk about the rest of the material we hadn't gotten through, namely motors and generators, transformers, and we can briefly say something about the grid. But that will complete the entire survey. So I'll begin by writing up the laws of electricity and magnetism again, and then I'll demonstrate what I have here for you, some little demonstration items. But we're applying the laws of electricity and magnetism. So first of all, we have electricity. Charge, electric field, and then also circuitry with currents, voltages, and power. So I'll just write voltage, current, power. So we had a bunch of applications, and this material we of course want to really be able to apply. To round out the discussion though, we also needed magnetism. Magnetism, we've got the properties of the magnetic field. One of the properties is that it's a vector field. We can put the arrow on top there. Magnetism and the B field, as I've said before, completely independent of the electrical phenomena, except that we then find that electric currents here produce magnetic fields. So you don't need a magnet, you don't need a solid object that you could call a magnet. If you have current going through a wire, you can have a magnetic field. So electric currents produce magnetic fields. And then we also have the fact that magnetic fields act on electric currents. They act on moving charges. That's the more general statement. B fields act on moving electric charges. And when we say act on, we mean there's a force involved, and that of course is the basis for our motors, electric motors. Finally, got this list of 5 here. We had Faraday's law with the magnetic flux. So changing magnetic flux, and that is phi sub B, produces a changing in time. Yeah, maybe I should specify that. Changing in time produces a changing potential. I'll write here electric potential, by which we also mean voltage. Okay. Yeah, once you have voltage, then you can have currents via Ohm's law, and you can just power your complete operation. So those were the laws of electricity and magnetism, and the application that we had was motors and generators. And I demonstrated those in the simplest possible form. Right, in the very simplest possible form, you've got this loop of wire, coil of wire. It's suspended or in a conducting frame. And I'll indicate that I have a handle here that I can turn. And I have magnets will indicate north and south pole that produce a B field that I'll indicate with these arrows there. And since this whole conducting frame, I'll just name these points A and B, if I turn this handle here, I'm going to get a voltage between A and B that we can just name delta V sub AB. So that was our generator. The motor was, instead of turning the handle, we put a battery in here and then we got the motor to spin. So yeah, if you really want to understand the motor and the generator in their very simplest form, which is what I demonstrated last time, and now I've brought them to us in a less simple form. So this is a little hand crank generator. Okay, hand crank generator, and everything, you know, is buried inside here. So what's inside here is coils of wire, magnet, and there's the handle, and I'm turning this thing. So why doesn't the propeller turn? Well, if I switch this on, I can get the propeller to turn. Now, this is a demonstration actually everybody has to feel, and we're not, right? We're not together for me to demonstrate this with every individual student. But what's so important to convince you is that when the circuit is closed, or in fact, how about I just disconnect a wire here? I'll disconnect both of the wires. What you experience is it spins very freely and easily. It's effortless. Making a little noise, but it's very effortless. When you hook it up and you get this machine to do something, you feel a corresponding amount of effort you have to expend to make it work. And the way it's really interesting is if you're cranking it and then people switch the switch off and on for you, because you just feel that surge of actually you feel that resistance, and you have to deliver a surge of power to get the thing going. That is, of course, energy conservation. In order to get the machine to go, you have to put in the effort on this side. Good. And so now we're talking about this crank again, the hand crank. Gives us the voltage there. We hook our wires up to whatever device we want to power. So what's powering this crank if not my hand? Well, this could be the generator in a power plant, and I'm actually running an entire thousands of kilograms of water per second through the generator in the hydropower plant. And then I can have, instead of just driving this little propeller, the entire civilization, or a big part of it. Okay, it's the same principle though. Good. So that's what I have to show right here. Very easy, flip and switch, a lot of work. Now this demonstration is kind of nice because you see I have an identical device here, and this one's a different color, makes no difference. These are both generators that will run that propeller, for instance, but what I'm going to demonstrate here is that whichever one I'm turning is the generator, and this one is the motor. So I turn the red handle and the white handle turns. If I turn the white handle, the red handle turns. And in fact, you can see I can go forwards, backwards. Okay. Same on both sides. So yeah, these are identical units. One's a generator. Well, they're both generator or transformer, depending upon, generator or motor, depending upon which one you are running. Okay, so that shows the equivalence of that device that I had the other day. Now with my tiny C-cell battery motor, I was not able to demonstrate it as a generator. Okay, that would have taken a lot more turns of wire. It would have been too faint of an effect, but I did demonstrate it as a motor. In future, I may work on the handmade generator, because the principle of this thing that I showed you is so transparent. In fact, if you build the thing and you're actually feeling all the little forces, then you are really getting full value. Okay, now these devices here are the last problem we have to discuss. So we'll make use of this, but I'm going to erase. I just mentioned transformers, so what we want to talk about is transformers. Now they actually depend on Faraday's law. So let's go ahead and have as our last new topic transformers. Now the idea here is that we're going to start with an alternating source. So instead of a battery, I draw this alternating source, and I'm just also going to label it delta V. I'll label it delta V sub 1. And it is the result of not hand cranking, but turning something, loop of wire, in a magnetic field. With a magnet, right. Okay, so that's the symbol for what we're doing over here. In fact, this delta VAV down here, that's what we're talking about with the V sub 1. Now, I'm not getting into the frequency because the voltage will also depend on how fast we're turning it, but we're just going to assume a particular speed of rotation. Okay, so what we want to do is get, say, this voltage, let's just say it's 120, we want to get it down to maybe 12. That would be a transformer, a step-down transformer, or maybe we want it to get it up to 1,000 volts or a couple thousand volts. So what we do is this. We wrap these wires around, let me draw here, I'll use another color. We're going to draw an iron core. We'll just draw a large one so that so this is a solid three-dimensional piece of iron. Okay. There we go. Solid three-dimensional piece of iron. And we're going to wrap the wires around it. These are all insulated wires. We're going to wrap it many times. So there we go. And we've wrapped it N, so let's write what we have here. Iron core. We have a total of N1 turns. So we have delta V sub 1 and we have N1 for the number of turns. And then over on this side we wrap around the iron core, and we have over here N sub 2. N sub 2 turns. And that's a transformer. There is no connection between this wire and this one here because this is iron, but this is insulated wire. So, insulated wire. Yeah, so what's happening here? We have alternating voltage, so we have alternating current in this wire. So alternating current. Well, we know that, I'll use red, we know that this current here produces a magnetic field, and an alternating current is going to produce an alternating magnetic field, that is to say a changing magnetic field. So there will be a changing magnetic field here, and the iron core serves to channel the magnetic field. So the magnetic field, which is being generated here, okay, will actually go around because of the iron and be very strong on the other side as well. So these magnetic fields, I'm going to draw a kind of circle here. They are changing in direction all the time, and what's our law? Faraday's law, changing magnetic field It's going to give us a changing flux through these coils here. And particularly on this side, we now have a changing flux. Okay, so changing V sub B. So we have a changing flux through the coil on this side, changing voltage over this on this side, and we're going to end up with delta V sub 2. And there's a very simple relation between these voltages. And we have delta V sub 2 here. This could be the, this could be the power plant. It could be a transformer. This could be the voltage in the walls of, wall of your house, and the plugs in your house. This could be the voltage right there, for instance. In which case, this would be 120, and this would be much larger. Okay, yeah, let me show you what we have here in terms of the real application. So this is the iron core. It's heavy enough, and we can complete it by putting this across and clamping it. Okay. Okay, so where are the wires? So the wires are here. So this one has some number of turns. Does it say so on it? I don't know the number of turns here. Okay, but this would be our N sub 1, and this here would be off to the alternating source. Okay, so N sub 1 would be right here. This plug represents going off to the alternating source. Now this one actually says how many turns it has on it. 23,000. Okay, so the wire's actually hidden under here, 23,000 turns. But same as this device, put that there and then clamp it. And we're going to have, the alternating source, the fields generated on this side, right? The alternating current generates the alternating field. It's on the left, and it ends up here on the right. And then if I were to plug in a couple of wires here, I would get my my voltage sub 2. Okay, a little more of a demonstration object. So you may have these on a lot of your household or electronic devices. Looks like this. It's a transformer. If you cut it open, what do you know? You see that metal core, and in this case, the coils are actually both inside, not on either side, but works this way too. But yes, metal core and a little bit of circuitry, and then the two different coils got a yellow and a red one here. Okay. So if you have a spare or something you're about to discard, go ahead and open it up, and you'll see what I was talking about right here. So this is just for demonstration purposes. Now, what's the relation between the voltages and the turns? It's very simple. We have delta V2 divided by delta V1 is equal to N2 divided by N1. Okay. Literally just the ratio of voltages here is the ratio of turns over here. And we'll finish up with a couple of examples. But I kind of like having this picture here. Okay, so let's keep that picture up there. This is the relation between this output voltage and this input. And now, if the number of turns was the same, then of course the voltages would be the same, and that wouldn't be what we're trying to do. So for safety, what we like to do is go from 120 volts down to 12 volts for these devices. They usually go from 120 down to 12. So that is called a step-down transformer. For example, when delta V2 is less than delta V1. Okay. In the example with the 120 volts, example delta V2 equals 12 volts, household, or what should we call them? Your basic electronic devices, household devices. That's mostly for safety. Okay. 12 volts won't do you any harm. If you've ever grabbed 120 volt by accident, it's pretty dramatic. Okay. And delta V1 is 120, so that's a household electronic. That's your household wiring. Household plugs. 120 volts. So yeah, to achieve that, you just have to step down. So you have delta V2 over delta V1, M2 over M1. It's going to be 1/10. Now what's interesting is that this device you have in your own home is a step down, 120 to 12, but you could get the idea to turn it around and then it would go from 120 to 1,200. So be careful if you do that. Okay? Be very careful. My next example though is a step up transformer. Step down transformer. Good, yeah, you have this example, household wiring 120, electronic devices, little radios and what have you. Down to 12, so you just have 1/10 the number of turns. That means this, for every 10 turns on this side, you just have 1 on that side. Good, so the next one is the step up transformer. Second point here, step up transformer. And that is delta V2 is greater than delta V1. Example, if delta V2 is to be 1,200 volts, start with 120 volts. You're just going to reverse this ratio. You're going to have 10 to 1 instead of 1 to 10. I'm going to put a question mark here. I'm not sure what you need a 1,200 volts for, so be careful. Okay. These things are typically encased in a shell, and so nothing can go wrong. But if you were to take it apart, you could reverse it and see what happens. Okay, and my final discussion point is for transmission over great distances. Transmission of energy over great distances, and then we'll actually be complete. So let's go ahead and erase this whole thing. So transmission of energy or power that's right, electric power and we're now going to transmit it over great distances. So you may have even tried to run some extension cords into the backyard for a party. You run them out, maybe 100 feet, turn the lights on and they're dim, okay? That's because you're losing voltage and hence power out at the, due to the length of the cords, of the wires. So how do we get around that? We have to remember the following. Let's just write our laws of electricity now. And we'll imagine we've got some transmission lines here. And here's our great distance. Okay, there's our tower. And we're doing them in twos, okay. They're gonna come down here, these are gonna go down there. So here's our great distance. Now the power equals I delta V. Okay. And you can say that's the power transmitted from point A to point B here. But there are going to be losses, and the losses are due to heating of these wires over great distance. So I'm going to write P loss is equal to I times, now delta V, R of the wire. Okay, remember delta V is equal to R times I. That was Ohm's law. Okay, so I plugged in Ohm's law. So this is the transmitted power, but this is not the same as the transmitted power. The loss, I'm referring to the resistance of the wire. So I'm supposing I've got this good current, but I've got resistance in the wire. So this power loss is the amount of heat that's being produced in the wire per unit time. So the loss is I squared R. Okay. Now, we want to reduce this quantity as much as possible, and if the resistance of the wire, when I say wire, I mean the transmission wire here. If the resistance is given, the only way we can reduce the loss is to reduce the current, okay? So to reduce loss, we must reduce current. Okay. But now we go back to this idea here. And how do we reduce the current? By increasing the voltage. So therefore, increase the voltage. And that's what we just had with our transformers. Increase the voltage. So if you can increase the voltage by a factor of 10, you can decrease, you can multiply the current by 1/10. But if you multiply the current by 1/10 and you square it, then you have I squared is 1/100. So you're really reducing the loss tremendously. So in order to effectively transmit electricity over great distances, we need to substantially increase the voltage. And in fact, what they'll do is increase it to 100,000 volts. Okay, so instead of 120 up to 1,200, all the way up to say even possibly a million, but 120,000 volts for sure. Okay, and so you have 120,000 volts here, correspondingly smaller current, correspondingly much smaller losses. Tiny fraction. In fact, without that high voltage, you're not even going to be able to get current over those great distances. The losses will just dominate. So that is what's done, and what you'll have here is your power plant, and it'll generate what it does, and then you're going to step up transformers here, and then down here you'll have step down, so you can get it back to 120 volts in your house. Okay. More than one, but there will be substations where this is done. Good. That's the basics. Increase voltage. Yeah, that's what we're going to leave now. Let me consult the clock. Okay, good. So in our last hour, we'll just do a necessary review, complete review, as much as we need, and I'll give you a good heads up on all the problems on the final exam, and that'll be it. See you then.